Now, then after that, you move on to the next page. This one is regarding electromagnetic induction. Now, you would have an EMF induced inside a conductor whenever there's relative motion between a conductor and a magnetic field. When you have an induced EMF, this in turn causes an induced current to flow inside the conductor. Now, EMF and current are two different physical quantities. EMF is actually referring to your voltage. Current is really referring to current itself. So they are actually two different physical quantities with different units, but they are closely related. When you have voltage, you're going to have current and vice versa. Okay. So here, if you wanted to have an induced EMF, induced current, you need to have relative motion between a conductor and a magnetic field. So it does not matter whether the conductor is moved through the field or the magnet is moved past the conductor. An induced current will still flow in either case. When your motion stops, both induced voltage and current will then drop to zero. So the diagram below here shows you two different examples of electromagnetic induction. First, you have a wire and a magnet. The second one, you have a magnet and a core of wires, or rather a solenoid. So in both cases, you try to move one of them while the other remains stationary. So for the first diagram, the long wire is moved up and down between two magnets. It produces an induced current. And then after that, for the second case, a bar magnet moved in and out of the solenoid also produces an induced current. You can detect the induced current if you were to connect an ammeter to the wire and solenoid respectively in each case. So right now you notice that the wire here is actually connected to an ammeter, and the solenoid here is actually also connected to the ammeter. You need to connect your ammeter to the conductor because your EMF induced causes current. Current can only flow inside a conductor. So your ammeter must be connected to your conductor here, not the magnet. Okay. So right now, if you see a deflection of your ammeter needle, it tells you that there's induced current flowing. If you have a faster relative motion between the conductor and the magnetic field, it would tend to produce a larger deflection of the ammeter needle, and hence it tells you you have a larger induced current. Now, when your direction reverses, the direction of needle deflection actually also reverses too. What we mean by that is, for example, if your wire here, you move it downwards, you could see your needle deflection going in this direction. But the moment you go and pull your wire upwards, the needle deflection goes the other way. The same could also be said when you try to use a magnet and push it in and out of your solenoid. You push your magnet into the core, your deflection goes this way. But then when you pull it out, the deflection goes the other way. So when the direction of your motion reverses, the direction of needle deflection reverses. And this also tells you that the direction of your induced current has actually reversed. So why is it that when you have relative motion between your conductor and your magnetic field, you have an induced EMF in the first place? What actually caused the induced EMF and induced current? So if you relate to the first case here, when you were moving your wire in and out of your magnetic field, what actually happened was that your wire was actually cutting across the magnetic flux of the magnets. So these were your magnets, isn't it? So the magnets actually had their own magnetic field, like this. So as your wire moved in and out, it was actually cutting across the magnetic flux or magnetic field lines. So the diagram that you see here is actually showing you something like that. Your wire, as it moves, is actually cutting across your field lines or flux lines. Okay, so the act of you cutting your magnetic flux is what gives you your induced EMF as well as your induced current. So here in the diagram, you're moving your wire in this direction, you're cutting your magnetic flux in this direction, you can get induced EMF, induced current in one particular direction. But the moment you go and move this other way, you're cutting the magnetic flux in the opposite direction, you're going to get an induced EMF or current in the opposite direction too. So here in the next point in your notes, it was mentioned to you that if you remove the wire from the field, it again cuts your magnetic flux, but in the opposite direction. It's actually kind of referring to this one at the top actually. If you move your wire down, you're cutting magnetic flux. If you move your wire up, you're trying to move it out from the field, you're actually also cutting magnetic flux. But your cutting is in the opposite direction, so induced current is also in the opposite direction. So in summary, just know that cutting of magnetic flux by a conductor is what gives you your induced current inside the conductor itself. Then as for the second case, when you're trying to move your magnet into a coil, there is also induced EMF as well as induced current. But this time, rather than saying something about flux cutting, we talk about flux linkage. Just now, as I mentioned to you in the first page, flux linkage is really referring to the total number of flux across all the coils. So consider this, when you have a coil with many turns that is outside a magnetic field, there's actually no flux linkage through the coil. Say for example, right now, you look at the diagram here, this is your coil, your solenoid. At this point here, it could be that your magnet is not inside the picture. Your magnet is very far away. So you only have the coil here. In this case here, there's actually no flux linkage because there's no magnetic field present. But then let's consider that this time, you try to bring a magnet close to your solenoid or your coil here. So this is akin to you bringing your magnet into the solenoid, like the second example diagram over here. When you bring your magnet close to the solenoid, what will happen is that your magnetic flux from your magnet will actually pass through your solenoid. So this actually causes you to have flux linkage because you have the magnetic flux passing through multiple areas inside your coil. So there is actually flux linkage through the coil once the solenoid is inside the magnetic field of the magnet. So what happens now then is that if you were to move your coil in and out of the magnetic field, or you were to move your magnetic field in and out of the coil, this actually changes the flux linkage through the coil, and this induces a current too. So here, in your case, rather than relating to flux cutting, which causes induced current, you relate it to changes in flux linkage that causes the induced current. So both cases here will give you an induced current. Either it's through flux cutting or either is through flux linkage change. Now, there will also be some other cases where you notice that there's actually no relative motion between your conductor and your magnetic field. That one would be more for if you're talking about a transformer. An EMF would also be induced if your conductor is stationary, but inside a changing magnetic field. So the example is a transformer where you have a primary coil that produces a changing magnetic field that links to your secondary coil. So when you're talking about transformer, a transformer usually has a primary coil like this and a secondary coil at the other end like this. All right. If you were to let current run through your primary coil will produce its own magnetic field, and that magnetic field produced by your primary coil would actually link to your secondary coil in a manner that is similar to this. So the thing here is that when your primary coil current is changed, your magnetic flux produced by your primary coil also change. So that magnetic flux that was produced here was already linking to your secondary coil in the first place. So over here, if your magnetic flux at the primary coil change, it also would mean that the magnetic flux at the secondary coil would have changed too. So since your secondary coil here is experiencing a change in flux or also a change in flux linkage, you're going to have an EMF or current induced too. So as secondary coil experiences a change in your magnetic flux linkage, an EMF and thus current is also induced inside your secondary coil. Here for secondary coil, sometimes we say flux, sometimes we say flux linkage is the same thing. Flux refers more to the part where you're talking about the magnetic field lines. Flux linkage refers more to the flux passing through all the cores. They're actually talking about the same thing. So for this case, no relative motion between your conductor and your magnetic field, but because there's change in magnetic flux linkage, again, you have induced EMF as well as induced current.